Welcome back to Algebra 2, Topic 37, Natural Logarithms. Now this is logarithms dealing with a base of e instead of 10. And this is part 1 of the video, where we will explore the properties of natural logarithms, as well as how to evaluate natural logarithms. So first and foremost, what is a natural logarithm? A logarithm with base of e, so log base e, is often denoted by log base e of x or just ln of x. Now here, the common base is e, or Euler's number. Euler's number is an irrational number. It's 2.718 ... So it goes on forever. So instead of dealing with a base of 10 like we have in the past with logarithms, we're dealing with e instead. So all of the properties that we have dealt with regular logarithms also apply to natural logarithms. Here we have the product property, the quotient property, the power property, where when we have an exponent, we bring it down in front. We also have the natural logarithm of 1, which is basically saying because we can rewrite every natural log as ln base e, although it's usually omitted, as e to what power gives us 1? Well, we know that any number to the 0th power gives us 1, hence why this will equal 0. Now when we have ln base e of e, that is always going to equal 1 because this is saying that e to what power gives you e. Now we know whenever we don't see an exponent, we automatically write a 1. So this is telling us that our unknown here is 1. Now with the change of base formula, we've seen this with regular logarithms of log base 10, where we have log base c of a is the same thing as log base 10 of a divided by log base 10 of c. However, this also applies to natural logarithms. If we have ln base c of a is the same thing as ln base e of a divided by ln base e of c. And we can actually interchange them, so we can use them both ways. If we see a log of a base in a number, we can also apply the natural log when using the change of base formula, and we'll get the same answer. So for example, if we have, let's say we have log base 2 of 7, and that gives us, if we apply the change of base formula, log of 7 divided by log of 2. Now, what if I told you, well, I wanted to find the natural log of base of 2 of 7? We can rewrite that as ln of 7 divided by ln of 2. And again, notice here that my bases are e here and my bases are 10 here. So let's just plug it in to make sure that they're actually the same. So if we have log of 7 divided by log of 2, that gives us 2.807, etc., etc. Now let's try with a natural log. So if we have ln of 7 divided by ln of 2, we also get the same value. But notice here, if I were just to compare my numerators, for example, let's just identify what's the log of 7. That gives me 0.845. Let's try the ln of 7. That's 1.945. So here we have different numerators, however the proportion is the same between the log and the natural log. We have different numerators because we're dealing with different bases. We're dealing with base of 10 or Euler's number for the natural log. So even though they might look different when you plug in them separately for numerators and denominators, the overall answer in the end will be the same. So they will both equal 2.807. And that's because we have the same proportions. So let's go into evaluating some examples. ln of e. Well, we know automatically that my base is e, even though it's usually omitted. So this is the same thing as ln base of e of e. Well, we know from my property that ln base e of e is 1. So my answer here is 1. Now what if I take the natural log of 0? Will I get an answer for that? That's the key question. Here, this is actually undefined. And that's because if we look back to our topics dealing with regular logarithms, logarithms only deal with positive numbers. 0 is neither positive nor negative. So it's undefined. So we can only take the log of positive numbers. Now what about ln of e to the 5th power? So we could do this two ways. If we use the power property, we can bring my exponent out front and get 5 times ln of e. Now we know from number 1 that ln of e is 1. So we get 5 times 1, which would just give us 5. Now another way that we could do this is we could think of this problem as, well, this is basically saying, because this is ln base e, that e to some power gives us e to the 5th. Well, the only way to make that true is if my answer was 5. So there's 5 again. Moving on to number 4, we can also use the power property and bring our exponents down in front. So we end up getting negative 3 ln of e plus 12 ln of e. Now again, looking back to number 1, we have ln of e and ln of e. We know that ln of e is 1, so this is the same thing as negative 3 times 1 plus 12 times 1. Negative 3 times 1 is negative 3. 12 times 1 is 12. Negative 3 plus 12 gives us 9. Moving on to our next example. So if we have ln of 1 divided by e to the 24th power, what is another way that we can rewrite 1 divided by e to the 24th power so that we're not dealing with a fraction? Well, we can rewrite this as ln of e to the negative 24th. And using our power rule, we can move our exponent down front and get negative 24 times ln of e. Now again, we know that ln of e is 1. So negative 24 times 1 gives us negative 24. Another way that we could write this is if we wanted to use the quotient rule. So if we have ln of 1 divided by e to the 24th, that's the same thing as ln of 1 minus ln of e to the 24th. We know, again, that ln of 1 gives us 0. So plugging in, we get 0. Now here, ln of e gives us 1. We can move our exponent down and get 24 times ln of e, which also gives us 1. So we get 0 minus 24, which is negative 24. So you can do it either way with that problem. For number 6, we have ln of e squared raised to the 6th power divided by ln of e cubed raised to the 4th power. So if I'm asked to simplify here, what do I notice first? Well, I notice that they both have ln of e. And I know that ln of e can be simplified. So if I bring my exponent down in front, let's deal with within my parentheses first. I would get 2 times ln of e raised to the 6th power over 3 times ln of e to the 4th power. Now we know that ln of e and ln of e are just 1. So if we simplify this, we'd get 2 times 1 to the 6th power over 3 times 1 to the 6th power, which would just give us 2, I'm sorry, that's not to the 6th power, that's to the 4th power. We get 2 to the 6th power divided by 3 to the 4th power. 2 to the 6th power is 64, and 3 to the 4th power is 81. Last problem, we have ln base 3 of 6. If we're asked to evaluate this, we can use the change of base. And we can evaluate this as either log of 6 divided by log of 3, or we can do ln of 6 divided by ln of 3. Whatever floats your boat. So if we evaluate that, let's deal with ln. So we have ln of 6 divided by ln of 3. We get 1.631 if we round it to the nearest thousands. Now let's just double check that taking the log would give us the same answer. So log of 6 divided by log of 3. Same answer, 1.631. And that's it. Thank you for watching.